Hi, good morning, people. So we're gonna start, as I said, with the class that we have today. Remember that we were talking already about fluid mechanics, in this case, fluid at rest. So that's necessary. We're going to continue doing the exercises that we had and also review a few things along the way. Um, let's watch the next video. Oh, hi, everybody, by the way, people that I have not seen. So let's share it right away. And then remember, pay attention to the video. It is talking about uh, a very important tool in fluid mechanics. So please pay attention. And then I'm going to select people to participate, or if you want to participate, we're open to that. Let's do it very quick in here. This is a TED Ed video. So let's see it.
Aristotle famously said, "Nature fears of empty space," when he claimed that a true vacuum, a space devoid of matter, could not exist because the surrounding matter would immediately fill it. Fortunately, he turned out to be wrong. A vacuum is a key component of the barometer, an instrument for measuring air pressure. And because air pressure correlates to temperature, and rapid shifts in it can contribute to hurricanes, tornadoes, and other extreme weather events, a barometer is one of the most essential tools for weather forecasters and scientists alike. How does a barometer work, and how was it invented? Well, it took a while. Because the theory of Aristotle and other ancient philosophers regarding the impossibility of a vacuum seemed to hold true in everyday life, few seriously thought to question it for nearly 2,000 years, until necessity raised the issue. In the early 17th century, Italian miners faced a serious problem when they found that their pumps could not raise water more than 10.3 meters high. Some scientists of the time, including one Galileo Galilei, proposed that sucking air out of the pipe was what made water rise to replace the void, but that its force was limited and could lift no more than 10.3 meters of water. However, the idea of a vacuum existing at all was still considered controversial, and the excitement over Galileo's unorthodox theory led Gasparo Berti to conduct a simple but brilliant experiment to demonstrate that it was possible. A long tube was filled with water and placed standing in a shallow pool with both ends plugged. The bottom end of the tube was then opened and water poured out into the basin until the level of the water remaining in the tube was 10.3 meters. With a gap remaining at the top and no air having entered the tube, Berti had succeeded in directly creating a stable vacuum. But even though the possibility of a vacuum had been demonstrated, not everyone was satisfied with Galileo's idea that this empty void was exerting some mysterious yet finite force on the water. Evangelista Torricelli, Galileo's young pupil and friend, decided to look at the problem from a different angle. Instead of focusing on the empty space inside the tube, he asked himself what else could be influencing the water. Because the only thing in contact with the water was the air surrounding the pool, he believed the pressure from this air could be the only thing preventing the water level in the tube from dropping further. He realized that the experiment was not only a tool to create a vacuum, but operated as a balance between the atmospheric pressure on the water outside the tube and the pressure from the water column inside the tube. The water level in the tube decreases until the two pressures are equal, which just happens to be when the water is at 10.3 meters. This idea was not easily accepted, as Galileo and others had traditionally thought that atmospheric air has no weight and exerts no pressure. Torricelli decided to repeat Berti's experiment with mercury instead of water. Because mercury was denser, it fell farther than the water, and the mercury column stood only about 76 centimeters tall. Not only did this allow Torricelli to make the instrument much more compact, it supported his idea that weight was the deciding factor. A variation on the experiment used two tubes, with one having a large bubble at the top. If Galileo's interpretation had been correct, the bigger vacuum in the second tube should have exerted more suction and lifted the mercury higher. but the level in both tubes was the same. The ultimate support for Torricelli's theory came via Blaise Pascal, who had such a mercury tube taken up a mountain and showed that the mercury level dropped as the atmospheric pressure decreased with altitude. Mercury barometers based on Torricelli's original model remained one of the most common ways to measure atmospheric pressure until 2007, when restrictions on the use of mercury due to its toxicity led to them no longer being produced in Europe. Nevertheless, Torricelli's invention, born of the willingness to question long-accepted dogmas about vacuums and the weight of air, is an outstanding example of how thinking outside of the box or the tube can have a heavy impact.
Okay, so big question. Tell me your thoughts, your conclusions about this video that we just watched. Who wants to start? Remember that video was about barometer, right? Which is almost the last exercise that we had. You have seen that type of instrument already. And why is it possible to have this? Let's ask some people then. Cesar, go ahead.
I will say maybe because the pressure of the water inside the the thing, you know,
The tube.
and and the pressure of the air, the external air,
Mhm.
acting in the water.
Yeah, that's true. That's why you have that phenomena, which is great. Isabella, about the video, conclusions, thoughts.
Okay, so every invention it comes with a necessity, and the first necessity that I saw it was that they were trying to like get out water from el pozo. I don't know how to call that, but they like dedujeron that they couldn't do it, so they just started inventing, and they carried the barometer, and it was supposed to like calculate how much oxygen, I guess, or like how much air there was between like the vacuum that they were saying.
That is correct. And as you can check, something happened when that person went up to a hill. Something happened to the pressure. That's what they explain. Can somebody tell me about that and why is that possible? Filippo, go ahead.
In the experiment he did before, he saw that when the atmospheric pressure and the pressure that was in the water, like inside the thing, it could go higher. When he went to the mountain, there was more, I think, atmospheric pressure, and that was why it would, como el agua llegaba, no el agua, el mercurio llegaba menos alto or less
Great.
atmospheric pressure. No sé.
Yep, that is correct. And that's why they use water at the beginning. You know that water has a specific density that is used a lot. Actually, water is the fluid that you will see that people, scientists study a lot to see how fluids work. And the density was perfect. You saw what happened with mercury, right? That almost spills out of the basal of the instrument, right? Because it's denser. Then the pressure of the atmospheric, well, the atmospheric pressure was not high enough to contain it inside. So that happens. So that's good that we talk about this because, as I said, we have an exercise which is about that specific uh, Torricelli's instrument. So let's go ahead and continue doing our analysis with um, with the exercises that you have for your physics project. Let me share. Okay, so let's share what we have in Jamboard now. Okay, so you have, I think it's on its way to be shared. I'm not mistaken. Yes, it is. Now it's on its way. So remember, these are the formulas that we have pre-set up, fluid mechanics. Pay attention to them because we're going to be doing, as I said, more exercises, and those exercises will contain more formulas to use. Uh, so we did that. Basically, the exercises that we have been doing, they were for solids. So checking density, checking mass for solids. We're gonna see one last one about solids, and then we're gonna move on to fluids. So let's see. I need somebody to read this exercise, please. Who wants to do it? Who wants to read that exercise? You're raising your hand, I'm not seeing you. Oh, Filippo, go ahead.
A 50-kilogram woman wearing high-heeled shoes is invited into a home in which the kitchen has vinyl floor covering. The heel on each shoe is circular and has a radius of 0.500 centimeters. A. If the woman balances on the heel, what pressure does she exert on the floor? B. Should the homeowner be concerned? Explain your answer.
Perfect, thank you. So yeah, that could happen in reality. So we have that specific floor covering. So should you be concerned if you had that scenario at home, right? So pay attention to the data that we have, the context, and then uh, just try to make your approach then I'm asking some people to explain their approach. Okay, so I'm gonna give you 1 minute for that. So well, very important to understand, right? That we have the mass that is being exerted by the woman to the vinyl floor, right? And then we have the radius of her heel, which is the big question. How are we going to solve part A? And how are we going to deduct part B? Okay, so if you have any idea, go ahead. Okay, Annabella, go ahead.
Okay, so the first thing I did was to get my data out. We have mass, we have radius, and we're missing the pressure. So the first thing I did, I don't know if I'm correct, is to look for the area of the heel. And then you just use a formula in which you multiply the mass times the area, and then I think there you can have your result.
Okay, okay. So that's a good one. So that way, multiplying the mass and the area, are you gonna get the pressure? Which is actually the big question. If the woman balances on one heel, what pressure does she exert on the floor? Right? So that will be at the end. Remember, the units should be in pascals as it is uh, the pressure. So Anabella, oh, by the way, for everybody, we are, as you're able to see, on page 6 of our Jamboard for physics, for the physics class. So Anabella, go ahead and do that first part at least so we can see it. We are on page 6.
On Jamboard.
Yeah, on Jamboard. Do we have any other approach or do you agree with that one? Okay, so it seems like everybody is on the same path.
Teacher, you need to give me access, please.
Oh, okay, let me just see it. Let's see. Okay, Anabella, yes, you are a viewer, that's true. So, editor. Okay, there you go. Refresh, please.
Teacher, I think I first have to convert it. O sea, no tengo que convertir, like, from rule of
You should. You should,
right?
because, yeah, you should.
Instead of, o sea, para poder ponerlo en el paréntesis when I'm multiplying the area, right?
Exactly. So, yeah, you will need to transform what you have. For example, remember that in the formula, you're going to have something that is in meters. So try to transform that radius that is in centimeters into meters, knowing that there is 100 centimeters in 1 meter. That means that you will need to divide by 100, right? So what will be the acceleration that you're going to use there?
Yeah, that's the thing. I have to find it first.
No, you don't need to. Actually, it's in the exercise. Think about it. Where is this, like, is this force being exerted vertically or horizontally? Because it's the heel making pressure. So what you have is something like this. Can I erase this P? I'm gonna make like the little free body diagram right here so you see what's going on. What we have is a heel, right? That's like the heel, let's say that's the shoe. Okay, so what happens is that you have a pressure being exerted into this direction. So I do agree that that pressure is a force being exerted into the y direction. Remember, what is the acceleration every time we move in vertically? Can somebody tell me that? What will be the acceleration? Yes, Mauricio.
9.81.
Very good. So there you have it. So your acceleration is actually gravity. Very good. Thank you, Mauricio.
Meters over seconds, right, teacher?
Yeah, meters over second squared, which is the unit of acceleration.
Done, teacher.
Perfect. 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 So it seems like you solved the riddle. What do you think, guys? So at least the first question is answered. That has been answered. So what would be the pressure exerted by the heel to the floor? That's that number that you have right there, which is a very big number. It is an approximation of 6113 times 10 to the power of 6 pascals, or 6,131,250 pascals. Now, how could you answer part B? Should the homeowner be concerned? Explain your answer. Like, you just need to explain it, okay? There's no calculations involved there.
He
So,
doesn't have to be concerned, but I don't know how to explain it.
okay, interesting. And I have somebody else. So Annabella said that the homeowner should be concerned. I think she's referring to this
No, no,
pressure.
no. He
Right?
shouldn't. He shouldn't. I think
Oh,
he
okay.
shouldn't.
Okay. Why? Why? I know that you said you don't know how to explain it. But why do you think that person shouldn't? And then Alejandra Vivas, which raised her hand.
I don't know, teacher. Like, I don't know how to. I don't know.
You don't know how to explain it. That's okay. Alejandra, help.
I think it's because well, Navera's trying to say that even though it's you see like this big number of pressure,
Hmm.
maybe that isn't enough, to break or damage the vinyl floor. I mean, it's not that fragile. Maybe that's what she's trying to say, and that's the only way I can figure out to explain why he
Very good.
shouldn't be concerned or be concerned. That depends
Very
on the
good.
fragility of the vinyl floor.
That is correct. I think that depends. That's the correct answer. Can you answer part B? Well, that depends. That depends on the pressure that the vinyl floor could support. So I think that's the answer. The only way that this homeowner should be concerned, that's if the pressure exerted by the heel is greater than the pressure that the floor could handle. That's the only way. Is that possible? We don't know. We don't have that info, but that's the only way that that person should be concerned. So that's perfect. Thank you. Good analysis, people. So we did that exercise. Go ahead and copy that, please. We'll give you 1 minute. And tell me if you have any questions meanwhile. So do you have any questions about this exercise? Let me know, please. So just remember, as soon as you have a question, a word problem, and a question inside a word problem, pay attention to some key points that are going to help you solving that. For example, data should be like the first thing that you should do. Questions, what do you need to respond so you don't over respond something or you get short on responding. And context. At the end, you should check the context because sometimes there are contexts there that you need to take in consideration. Okay, should we move on? No, not yet. Okay, some people are saying no. Okay, so let's copy that. Okay, so the big question, does this answer make sense to you? Right? It makes sense. And the part of B, remember, well, that person should be concerned only if, that's the big if, right? So this is like how we solve part A. And part B should be only concerned if the pressure of the heel is greater than the pressure that the floor can handle, right? That would be like, yes, I should be concerned if that's the case. Well, yeah, I don't know. So that's kind of another type of exercise. But B is just asking you, plain and simple. Okay, so should we move on to the next one now? Should we? Cesar, sorry. I'm gonna like ask you because you were part of the people that said no.
Oh, if okay, you can, yeah, you can
Okay,
go.
thank you. Thank you. Let's see this next exercise. I know that we are almost done, but at least let's read it and have an analysis on it. Okay, so Alejandra Vitiello, can you please read this exercise, please?
Mhm. A barrel contains a 0.120 meter layer of oil floating on water that is 0.250 meters deep. The density of the oil is A. What is 600 kilograms uh, times meter cubed? The gauge pressure at the oil-water interface. B. What is the gauge pressure at the bottom of the barrel?
Thank you so much. So you have there two questions, right? What is, um, okay, this exercise is a little bit, it has a typo on it because it says the density of oil is, and that's the number that you should have there, the 600 kilograms over meter squared. Like that 600 kilograms over meter squared is supposed to be right there where it says the density of the oil is. And then the question is, what is the gauge pressure at the oil-water interface? And part B, what is the gauge pressure at the bottom of the barrel? So in order for you to understand this exercise, I will say it will be very necessary for you to do a free body diagram of what's going on, a little bit, a little drawing, right? So let's do it in here before I like ask you for your analysis. So you have a barrel, right? And something is happening there. I have water and oil. I'm gonna ask you something. You have a liquid because it says like the barrel contains 0.120 meters layer of oil floating on water that is 0.250 meters deep. So which one should go above and at the bottom? Like which liquid? I have
Isn't
two,
oil
right?
supposed to be on top?
Which one?
Oil? Isn't oil
Yep,
supposed to be on top?
it is. According to what we have there, that's actually what's going on. So 0.120 layers of oil, and we have a little bit more of water. That's why. So we have an interface there, right? That's the interface that this exercise is talking about. So that's oil, and that's water, right? Okay, let's do it in blue. Let's color code everything. That's water. Okay, so we have that. We have also, like in here, we have like 0.120 meters. And here we have 0.250 meters. That will be the layers that we have. So at least this will give us an idea. And the information is what is the gauge pressure at the oil-water interface? What is the gauge pressure at the bottom of the barrel? Do we have a gauge pressure formula? Think about it. Do we? Or is it gauge pressure inside a formula that we can solve for it? Look it up and tell me. I need somebody to tell me. Do we have gauge pressure inside any of the formulas that it was given to me? Saida?
We have it in Pascal law.
Very good. So if we go back, oh, okay. If we go back, we do have gauge pressure. Actually, in Pascal's law, we have gauge pressure right there. Gauge pressure is equals to, which is this only portion that we have right there of that specific formula, that will be equal to, this is gauge pressure, remember. So that one says that you will need to multiply the density by the gravity by the height. So what do we do with these two other pressures? Well, the question is, what is the gauge pressure? That's everything that I want to know. So I will say that will be the approach for that exercise, which we are going to continue doing next class, but I think you have an idea of it, which is very, very important. So before we close the class, do you have any questions in general about these exercises? Do you have a question about this exercise that I have here pending? No? Like we're gonna see it next class, right? But think about it. Think about how could we solve this problem that we have right there. We need to know the gauge pressure at the interface, which is right here. And I want to know the gauge pressure in here. A little bit of investigation that I'm gonna leave for you. What is gauge pressure? Don't answer that. That's gonna be next class. And I'm gonna be asking people as well. So that will be the big question, and I'm gonna put it right here. So you remember. What's gauge pressure? Oh. What's gauge pressure? So that's the question. So you will answer that. That will be like the first question that I want to have an answer on next class. So if there is no more questions, actually I'm going to stop sharing now, okay? So if there is no more questions, today we were able to check a lot of things, as you were able to see. Like we checked what a barometer is, which is the next exercise, by the way, as you were able to see there. And we were able to get, an exercise about pressure on solids and now pressure on liquids. So the big question is, what is gauge pressure for next class? If there's no questions, I will say the class is dismissed. See you next class. Have a good day.
No, your teacher.
Bye.
Bye, Eric. Take care.
Bye. Take care.